Welcome back to my channel. We're going to take a look at an example of a telescoping series. So our example, we're actually going to be able to figure out the value that this telescoping series converges to. So this is definitely not the case with all series. In fact, most series, you're not going to know what they converge to. But for a telescoping series like this one, we'll actually be able to find that limit. So how do we do that? Well, our series is starting from 1 to infinity. So we can see from the index, k starts from 1, it goes to infinity, so we have a series. And the formula for the sequence terms of the series are 1 over square root k plus 1 minus 1 over square root k plus 3. So how we do this in general for a telescoping series is we're actually going to need to write out the sequence of terms. So what you might remember is that a series is a sequence of partial sums. Okay, that's going to be useful for us to know because if we can write out a formula for the sequence, then we can take the limit of a sequence, which is the thing that we actually can do versus with a series. If you can't do this process, you can't always know what it converges to. So let's write a formula for our sequence of partial sums. To do this, you just kind of start out and write a couple of the partial sums down. So we use the convention capital S to let it be known that it's a partial sum. So to figure this out, that means you're going to add all the indices less than 1. So since the series starts at 1, S1 is going to be equal to just what we get when we plug in k equals 1. So we would get 1 over root 2 minus 1 over root 4, which is 2. Okay, and there's no way, we don't really need to simplify that any further. Let's take a look at S sub 2, so our second partial sum, and we're going to have copying from our first 1 over root 2 minus 1 half. Now onto that, let's use a different color. We're going to add in k equals 2. So now we're going to add what we get when we plug in the index k equals 2. So that would be 1 over root 3 minus 1 over root 5. And then we're going to check and see, is there any way to simplify this? No, nothing cancels. We could combine it to one fraction, but in general, when you're trying to write the formula for a sequence, you want to observe patterns, and sometimes combining these fractions is not going to help you observe the pattern, so that's why I'm choosing not to do that right now. So let's keep going and see if as our sequence progresses, whether there's any patterns that start to emerge. So for S equals 3, we plug in k equals 3, but we're adding that on to what we already had. So 1 over root 2 minus 1 half plus 1 over root 3 minus 1 over root 5. And now let's plug in k equals 3 and add that on. So for k equals 3, we get 1 over root 4, which is 2, minus 1 over root 6. And check it out. We have some terms that cancel, so let me highlight those. Looks like we have a minus 1 half and a plus 1 half, and those are gonna cancel out. Nice. Okay, so let's see if that pattern's gonna progress and whether we can kind of write a formula. I think we probably need to write 1 or 2 more sequence terms out. So for the S sub 4, our fourth partial sum, we have 1 over root 2 plus 1 over root 3 minus 1 over root 5 minus 1 over root 6. And now we're going to plug in, let's use a different color, our k equals 4, and we'll get plus 1 over root 5 minus 1 over root 7. And what do you know? Our minus 1 over root 5 and positive 1 over root 5 will cancel. Okay, so let's take a look at our pattern. It looks that once we get high enough with our index values, there's going to be terms that cancel. So what's going to always be there? Let's highlight this. Let's choose. What's always going to be there for sure is going to be our first two terms. Those are never going to cancel because you're never going to have a larger k value that cancels with a 1 over root 2 and a 1 over root 3. If you think about it, we're plugging in k values that are bigger than 4 from this point forward, so you'll never have 2 and 3 pop up. So these are always going to be there. Okay, and it's not always going to be the case that 1 over root 6 and the 1 over root 7 are there, because if you look what happens, it looks like in the next s sub 5, the negative 1 over root 6 is going to cancel with a positive 1 over root 6. So we don't want to write 1 over root 6 and 1 over root 7 for our general formula. We want to try and write those in terms of n. So the 1 over root 2 and 1 over root 3 will always be there. But how do I write these in terms of the n value? Because those are changing. So if we look at what didn't cancel last time, it was the root 5 and the root 6 that didn't cancel. And this time it was the root 6 and root 7 that didn't cancel. So relate the root 6 and the root 7 back to the n value for that form. And remember that our n here was equal to 4 because that was our fourth partial sum. So it looks like what's going to be the case is we're going to have a minus 1 over root, and it would be the previous n plus 3. So it would be n minus 1 plus 3 will give me the 1 over root 6. And then minus 1 over the root of our current n plus 3. Okay, now we can actually go back and check. So for yourself, verify that this formula will produce for you the S3, S2, S1 as we go back in time. And if you want to check it with more n values, that's fine as well. But this is the general pattern for our sequence of partial sums. Okay, so this is our sequence of partial sums, and it is the case that our series, we'll just call it the series AN, is going to actually converge to the limit of our sequence of partial sums. And when we're talking about sequences, since n is always going to infinity, sometimes people will omit writing the arrow with n going to infinity because it's kind of implied. Let's take a look at what that limit is for this one. So the limit as n goes to infinity of our Sn is 1 over root 2 plus 1 over root 3 minus 1 over root n minus 1 plus 3 minus 1 over root n plus 3. So pushing the limit through, the only two terms that are going to be affected by the n are these last two, and it looks like the denominator of these fractions is approaching infinity, so the fraction as a whole is going to 0. So our limit would just be 1 over root 2 plus 1 over root 3. Okay, so that's the value that this series converges to. Pretty cool. And like I said, this is not going to be the case with every single kind of series that you can actually figure out the formula and find the convergence this way. But when you can, this is pretty much our most basic technique.